Hi everyone, welcome back to the course on Introduction to Material Science and Engineering offered by Edupedia World. Previous lecture we were discussing about the type of point defects that exist in a solid. Today we'll take the discussion further into other types of imperfections in a solid, namely the one-dimensional imperfections known as dislocations. So dislocation is a kind of a line defect, that is a one-dimensional defect, and dislocation can be of two kinds. The first is known as a edge dislocation and the other is a screw dislocation. We'll see what both of them are individually, but just to point it out that in addition to edge and screw dislocation, there is a third kind which is known as the mixed dislocation, which has component of edge dislocation as well as screw dislocation associated with it. So let's dive deeper and understand the concept of dislocation. A dislocation is basically a one-dimensional defect. As I already mentioned, it lies in one dimension, contrary to point defects which we discussed, which was a zero-dimensional defect. It was a point defect. In a dislocation, what happens is that the atoms surrounding the dislocation, let's for the time being assume dislocation is a line, right? Let's assume this is a dislocation. So therefore if this is our dislocation line, which is in one dimension of course, then the atoms surrounding this will have strain in it, right? This region will be a strained region, and as a result the atoms will not be located at its designated lattice site. Rather, they will be displaced from its original position where it should have been, and this displacement leads to a misalignment of the atoms surrounding the dislocation line. Suppose we have something like this. There is a plane of atom, extra plane of atom on the top, and the plane is missing downwards. As we will see in the next slide, that is how edge dislocation is there. So what will happen is there will be more atoms at the top and vacant places of absence of atoms at the bottom, right? Therefore more atoms has to be squeezed at the top, whereas less atoms has to be squeezed at the bottom. So there is a lot of compressive force at the top where there is an extra plane of atoms, whereas there are tensile stress where there is absence of the plane of atoms, right? This means that the atoms surrounding the defect are misaligned from its ideal position. Now, why do we study dislocation? What is so important about dislocation that we need to study it specifically? The idea is that all the defects influences the material property significantly, and dislocation is one of the defects which has most prominent effect on material property. As we'll see in future lectures, dislocation can be said to be the single characteristic which will define most of the properties of a material, other than the material itself, that is the atoms, the type of element making up the material. For a given material, the dislocation density, how the dislocations are arranged, that will have a very influential effect on the material property. That is why we need to understand the concept, basic idea about dislocation. And as I have drawn here, suppose we have a dislocation. This is normally, as we'll see, is called positive dislocation, denoted by this if the extra plane of atoms is at top. And suppose we have another dislocation line here such that there is an extra plane, half plane of atoms at the bottom, so that this dislocation will be bottom, right? Therefore, if this dislocation, the dislocations can move, right? In a crystal, in a specimen, the dislocations can move when stresses are applied. So if these two dislocations move and they come in contact with each other, then what will happen? This half dislocation at the top and this half, rather the half plane of atoms at the top and half plane of atoms at the bottom will combine together and the dislocations will get cancelled out, right? So opposite dislocations cancel each other out. That is what is meant. This is a positive dislocation, this is a negative dislocation. If they combine, then they will cancel each other out. This is one of the methods by which the dislocation density is reduced. Okay, so now that we have a rough idea about what a dislocation is, let us see the specific kind of dislocation, that is the screw dislocation and the edge dislocation. We'll start with edge dislocation. These two dislocations which I have shown here are examples of edge dislocation. Okay, so in edge dislocation, here is an example. As I said, for the edge dislocation to be present, there has to be extra half plane of atoms. So basically this is 2D and continues in the third dimension, that is within the screen and outside the screen. So this arrangement of atoms will be in multiple layers within the screen and outside the screen. Thereby this will be a extra half plane of atoms, right? Extra half plane of atoms, that is there are atoms present over here, but there is atoms absent here. Okay, so this is a positive dislocation, as I already mentioned, denoted with this symbol. Okay, so that is the definition of edge dislocation, the condition for edge dislocation, that there has to be an extra half plane of atoms. And this edge of the extra half plane terminates within the specimen, right? This is terminating somewhere within the specimen. The crystal continues and the half plane is over here itself. If this half plane goes to the external surface, then the dislocation will no longer exist, right? Because this becomes part of the external surface then. So for the dislocation, edge dislocation to exist, half plane of atoms should terminate within the crystal. Okay, and this line which demarks the presence of extra half plane and the absence of extra half plane is the dislocation. So this line, let me use a different color. So basically this line which we will have is the dislocation line. The line separating the half plane from the absent half plane is called the dislocation line, and in this case it is the edge dislocation. And as we have already discussed, the lattice distortion is present around the dislocation line. So let me see here what is happening. Here we see that there is extra atoms over here, therefore these atoms are squeezed for space. They have less space and more number of atoms, whereas here there is more space and less atom, one atom less in each line. So here there is a compressive regime. Okay, there are atoms pushing against each other, here the atoms are pulling against each other. Now an important criteria to understand what the edge dislocation is, or any dislocation for that matter is known as a Burgess vector. So what is exactly a Burgess vector? A Burgess vector reflects how much deviation from the ideal scenario is there due to the presence of dislocation. Okay, so let me show you. Basically, to draw the Burgess vector, you need to complete a circuit around the dislocation line. What do I mean by that? What I mean is, since this is the dislocation line, this going inside the plane of the screen is the dislocation line, we'll draw a circuit surrounding that dislocation line. We'll go same number of units in all the four directions. So let's say we start from this location. We go 1 unit to right, 2 unit to right, then 1, 2, 3, 3 units bottom. Now we have to go 2 units to left, right? Because we had gone 2 units to right here. So 1 unit, 2 unit, 2 units to left, and again 3 units top. 3 units top is this. Okay. Now what we see is, by going the same number of steps in anti-parallel directions, right, we have a mismatch. We started from here but we finish over here. Okay, so this mismatch from the finish to the starting point, this vector that we get is known as the Burgess vector, denoted by a B. So the Burgess vector for this dislocation is B over here. We can do and get the Burgess vector same even if we go any different number of steps. Let me show you an example. Let me go 4 cross 4. Okay, and let me start from a different location altogether. But keep in mind that the dislocation line needs to be covered while going down the circuit. So let's start from this location now and go 4 cross 4. So 1 step, 2, 3, 4. 4 to the right, 1, 2, 3, 4. 4 bottom, 1, 2, 3, 4. 4 left, and 1, 2, 3, 4. 4 top. So we have gone 4 steps, right, bottom, left, top. And what have we ended with? We have ended with the same length of the Burgess vector and same direction. Okay, so it does not matter how many steps you go, and you need to go the same number of steps in the anti-parallel directions, and you will end up with something which is the Burgess vector that is from the end point to the starting point, right? And the circuit you draw should be around the dislocation line. These are the conditions to find the Burgess vector. Fine. Now we see that the dislocation line is something like this. Okay, it is going inside the plane, whereas the Burgess vector is in this direction, that is on the plane. Therefore, for a edge dislocation, a very important criteria is that the Burgess vector is perpendicular to the dislocation line. For edge dislocation, Burgess vector is perpendicular to dislocation line. This is condition for a edge dislocation. When we will discuss screw dislocation, we will find out that for a screw dislocation, the Burgess vector is parallel to the dislocation line. That is what differentiates between a edge dislocation and a screw dislocation if we know only about the Burgess vector. Okay. Now, what does what we mean is that a reduction in stress for deformation. Okay, this is a very important statement which I have written here. Let me explain you. Suppose you have a perfect crystal. Okay, if you have a perfect crystal, all the atoms are at exactly the location where they are supposed to be. Okay, all the atoms are where they are supposed to be. There is no impurity, there is no vacancy, there is no dislocation. Now if we apply a shear stress, if we want to basically shear move the atoms apart, okay, that is if we want to deform the material, basically what I mean to say, then what we have to do is you have to break all the atomic connections, isn't it? You have to break this connection, this connection, this connection, all the pair-to-pair connection in a one particular plane. Only then a single step movement for the whole system can take place, right? So you need a lot of stress, a lot of shear stress to break the atomic bonds and move the atom by a single atomic distance, right? Therefore, a lot of stress is required for deformation if we have a perfect crystal. But thanks to dislocation, what can happen? Let's see this scenario. Suppose you are applying a shear stress. What can happen is that now instead of all the bonds breaking between the atoms, what can happen is just this bond breaks and this atom connects itself with this atom. Now this bond is broken, right? So basically the dislocation has moved one step in this direction. Next, this bond breaks and this atom connects with this, dislocation moves one step in this direction. And this one by one movement of the dislocation leads to the movement of the crystal as a whole in this direction. So you need not break all the bond pairs. You need not break all the bonds at a given time. You break only single bonds and the dislocation keeps on moving further and further, thereby leading to deformation. So what we see is the presence of dislocation is pivotal to causing deformation at reduced stress. So what are the informations we can gather from this? Some important information which we can get from this is that a perfect crystal, which is the ideal crystal, which actually never exists, if that existed, then the amount of stress, the amount of tensile stress for deformation, the amount of stress you needed to provide it to deform would have been very, very high, in the order of gigapascals. Whereas the presence of deformation in the material, the presence of dislocation in the material eases out the process of deformation. And deformation is very, very significant for formation of any material. As in, if you want to make some rod or some sheet out of any metal, let's say aluminium, then you need to deform it. Therefore, the presence of dislocation is pivotal to metal forming processes, as that leads to reduction in the stress. Fine. This gives you an idea about edge dislocation and the importance of dislocation in the properties of a material. We'll discuss it further in future lectures. Now let us get an idea about screw dislocation. In the edge dislocation, what we saw is that basically there is an extra half plane of atoms. In the screw dislocation, what happens that instead of extra half plane of atoms, what we do is we take a perfect crystal, we cut it halfway through, and then we shift it, shear it upwards, right? So basically this atom ideally should have been over here. This atom ideally should have been over here. So what we have done is we have cut it half till midway of a perfect crystal and then sheared it. Okay? And as a result, what will happen is that we will form a helical path. If we try to go around, complete a circuit, we go a helical path and we get a Burgess vector like this. Let me show you. So as we have already shown here, going some steps here, 4 steps, 4 steps, 4 steps, and 4 steps here. If you go, then basically you can divide it by 2 step and 2 step. Then basically what is happening is you have a Burgess vector like this, right? The end point to the starting point. And this Burgess vector here is parallel to the dislocation line. The dislocation line is like this here, right? Because this side of the crystal is perfect, this side of the crystal is not perfect, and thereby the separating line is the dislocation line, that is this, and this line is parallel to the Burgess vector. So for a screw dislocation, as I already mentioned beforehand, Burgess vector is parallel to dislocation line. And how do we get the screw dislocation? Basically by cutting the crystal halfway through and then slipping it 1 step or 2 step or any number of steps we want. And the helical path is traced by the atoms around the dislocation line. If we move around the dislocation line, we will keep on stepping 1 atom step downward if we have sheared it by 1 atomic spacing. Okay, so this is screw dislocation. Now here I have tried to show you how dislocations actually look like under a microscope. This is 1 micron. So 1 micron is like 10 power minus 3 millimeters. And these lines are actually dislocation lines. This is a silicon piece which has been properly polished and prepared for microscopic observation, and we see a lot of dislocations here. So what are the take homes? The take homes are that no crystalline material is dislocation free. If any material exists which is crystalline, along with the crystallinity comes imperfections, and dislocation being one type of imperfection will be present there. What are the different sources of generation of dislocation? The sources varies from the solidification process itself, the process where the solid material is actually being formed. A lot of dislocation is introduced at that time, to deformation processes like rolling, forging. Those kind of processes introduces a lot of dislocation, as well as some temperature fluctuations if present, that creates stress, and that leads to a lot of dislocation formation within the material. And in addition to screw dislocation and edge dislocation, if we have a dislocation which has both a screw component and an edge component, in other words, if a dislocation is neither perpendicular nor parallel to the Burgess vector, then the type of dislocation which we have is a mixed dislocation, which has a component of edge dislocation and a component of screw dislocation. So mixed dislocation can be said to be the third kind of dislocation. Okay, so this gives you a broad idea about what a dislocation is, what is the importance of dislocation, how exactly dislocation is formed, what exactly are the dislocations, how does it look under a microscope, and some glimpse into why is it important for a material to have dislocation, or what are the effects of having a dislocation. Right. With this, I will close the lecture today. Keep in mind that dislocation will keep on coming back throughout this course. Next up, we'll discuss about two-dimensional and three-dimensional defects. Till the next class, have a great day. Goodbye.